All right. Okay, I think we're all set. Before we start with the presentation, I'm going to just go over some of the things that would be nice to do in the background. So first up, in case you haven't already, do sign up for Cohere. It should take you about a minute, just needs an email. And once you are signed up, Cohere should redirect you to the dashboard where you will see an option for API keys. Once you click on the API keys option, you'll see a long string of numbers that you'll need to copy. And once you have that ready with you, just let me know in chat that things went smoothly. So if some of you could give me some confirmation that you were able to sign up for Cohere and generate an API key. That's not good. All right, so if you signed up, it should redirect you to a page that looks like this. My apologies for the link not working. Yeah. And if you're in this space and you click on the API keys option, it should take you to a space like this, where it will list all of your trial keys, and all you need to do is copy one of your keys and keep them ready for when we will need them. Okay. So let's get back to semantic search, which is our topic for today. And really what semantic search comes down to is how are nouns connected to each other? How do we utilize the connections between different entities in order to power our search? And when our user provides us with a long string of words in the form of sentences, what can we do to ensure that our language model or our search engine understands the relationship between the different words in a sentence? So semantic search is all about connections and connectivity and utilizing and teaching a machine how to utilize these connections in order to get us better search results for our queries. So semantic search, semantic, the word, one of the many things that it signifies is meaning. So it is the, in the context of linguistics, it is the study of words and meanings and how relations are built using meaning. And when in the context of search, it's a search system that is fetching us not just keywords, but context. Now, one of the things that we as users or we as generators of a search engine would provide is a archive of documents. One of the things that we will be doing is, building a mechanism that can allow all of this content to be sorted and processed somehow. And the third thing is we want our model to return an answer to a query that a user is providing us. So in order for semantic search to operate well, there are two things that we will need. One is we need the information to be accurate and related to the query. Okay, if our user is asking us about the price of apples, we would prefer that the answer involve the fruit and not the machine, for example. Second is we want our information to be ranked so that the information that is most closely related to our query is on top, and search results that are not so related as deemed by our search engine are provided later. So the ranking as well as accuracy are two main factors that we would want to keep in mind. Now, what would we need in order to build a semantic search system? The first thing that we would need is a way to explain language to our machine. This is something that would be powered by a language model. What is our language model using? It's using something known as embeddings, which I will get into. And it's the language model along with all of its components that is creating connections between all of the words in our query as well as in our documents. And one of the things that our language model is being powered by is all of the information about the target language that we have been able to acquire and process, right? So we've got vocabularies, we've got sentences, we've got all kinds of tags that are associated with every item inside our language model, and there's all kinds of connections and information that we will need. Next is we will need a data set with information. So yes, we have some understanding of language, right? We've told our machine how to process words, but what are we going to be using in order to power our search? That is the information that our system is going to search through. So here, this would be some kind of a language corpus or a data set. However, it has to be slightly pre-processed. We want it in a format that is query response, question answer, topic description. So we want our data to be formatted in a way that our model can learn how to match queries to information. And for this, we need our information to be in a slightly similar format. Next is we would need a user provided query. So while we have our system ready, what is motivating our system to provide us with responses is the human being who is asking the questions. If we want to represent a human language in a computer readable format, there's something as humans when we are provided with a whole bunch of words, there is some processing that we're doing in order to make sure that all of our adjectives and our nouns and our prepositions and our verbs are working together to give us meaning in every sentence. And this is something that our computer also needs to access. And so how this is going to be built is by accessing information on how words are connected to each other. And it is these connections that is going to build a map to the meaning, right? So our meaning in a very simple way, in the context of semantic search, meaning is is one of the things that it is relationships between words to one another. Next, we utilize a language model that is creating this map of meaning for us. And one of the things that it's using is syntactic tags as well as semantic tags. If you're interested to learn more about this, one of the initial workshops that we did here on Spacey would be a useful tool to look at. So once we have once we have access to different tags that can classify our words or put them in different contexts, we also need to make sure that we have some kind of a vocabulary. We want to make sure that this, no matter what inflection a verb has, whether it's present tense or past tense, it's calling the same word, so it's calling the same lexeme. And all of this is happening at the language model level. And once we have our machine readable formatting of language, we can move on to actually processing at the sentence level. Now, there's one key distinction here between semantic searches and keyword searches. Those of you who've used Google before, say, 2009, 2010, a lot of our searches were being powered by keywords. So what our model was looking for was words across different documents in the internet. And this was being done, I mean, as the user, you had the ability to use and or and other conditionals. You could tell your model to look for certain words, but exclude certain words from searches. So we were controlling our searches at the word level. But when it comes to semantic search, we are better placed to provide sentences and make sure that our model automatically uses every word in our query sentence and place importance on words which might be more useful, like the entities, and maybe ignore other words that may not be so useful, right? Now, one of the reasons why semantic search was such an exciting development was because it gave us the ability to disambiguate between contexts. So, Apple the fruit, Apple the company. We want Apple the fruit to be to have some kind of a search result that connects to peanut butter. We might not want Apple the company to return us a a match for something related to peanut butter. So that would be one thing. Next is our models became a lot more flexible, and so even if you did not provide exact query words, it was able to look at other words that were searched in a related manner. It was able to understand that understand hypernyms. It was able to look for synonyms. It was able to exclude antonyms. So there were all kinds of word relations that semantic search was able to preserve and use. And the third thing is that once search engine optimization became related to making money, so once people realized that if your page is ranked high on Google, it means more advertisement and more money. People were able to hack this system with keyword stuffing. So you could simply throw in a bunch of words randomly into a page and basically get the Google algorithm to rank that page higher. And semantic search was able to break through or cut through that those kinds of hacks because they were not looking for words; they were looking for relationships between words at the sentence level. Right. There are, of course, many limitations to semantic search. I will cover some of them, and I will leave you to explore the others. And one now, one of the reasons why NLP for all, like in our workshop today, I have a discussion on semantic search is that it's all of the building blocks for natural language processing that have gotten us to a point of being able to utilize semantic search. And it's something that also connects to discussions on large language models because of course, one of the things that is powering this is our ability to process language at a massive scale. And it is, of course, a much heavier system. So continuing a discussion on when not to use a large language model, if your use case does not require a heavy system where sentence level information needs to be processed, keyword searches are still great. And it would be a choice on your part to choose a keyword versus a semantic search when you look for what kind of search engine you'd like to use. Now, next, I'd like to start with a few definitions. Given the duration of this workshop, I won't have enough time to go into depth on each of these terminology. I believe that almost many of the terms here are going to require workshop sessions of their own. So just very briefly, the first thing that I will be talking about a lot is an entity. And very broadly speaking, our entity is just all the nouns scattered through a given text that the text is in a way talking about. Next is query, because we are talking about search. There's going to be a what are we searching for question, and that is the query, which in this case, a user is providing us. Next is vector representations. So we have our language model, and somewhere in the back end, our language model is taking human language, turning it into a mathematical representation of some nature. It's creating a little space where every word is assigned a set of numbers, and these numbers are going to help our language model find out which words are closer to which words, and that is one of the ways in which our relations are being created. Now, vector representations in the context of semantic search get used in the form of embeddings. Again, I believe Mithun touched on it briefly in the last workshop. Here, we're mostly going to be using embeddings, and so I'll go ahead and just briefly talk about this. First is when embeddings essentially take all of these vector representations and capture the relationships at the sentence level as well as the word level. So if I am providing a sentence, what time does the session start? there's some some relationship between every word in this sentence, and embeddings are a mathematical representation that's going to capture and help me understand what these relationships are. Right. So another thing that embeddings are able to do is tell me which words share meaning and which words are closer to each other. It's something that needs to be learned from data. So there's going to be some kind of training involved in order to create embeddings. However, we have a lot of pre-trained models for this. So uh, it's worth noting that this might be a solved problem. And then we have the main use would be to capture semantic content, capture relationships, capture patterns. And right, if I have a very small image here, just to indicate it, our model here is being fed a bunch of words. Our words are being turned into embeddings, right? And then from these embeddings, we're making a decision for how many of these dimensions are actually useful to our case. And finally, we have a graph where the words that tend to be close to each other in meaning are shown with arrows that are closer to each other, and words that are relatively distant from them are farther away. And there's something that I may not be able to cover today, but is a very fascinating topic in itself, is the semantic web, which is a representation of the World Wide Web. And it is a way in which all of the words, all of the language that has gone into the World Wide Web is made machine interpretable, and by making all of the information interconnected. So here we have a bunch of entities. The entities exist in more than one language, and all of these little arrows are ways in which the different information connect with each other, as well as the specific sources that help a model decide which entities are connected with which. So how did we get here? Again, a very heavy topic, but very briefly, some of the important developments in the context of Google that helped us get to a semantic search position where we can use AI to give us information in a question answer format. One of the things, the information that existed out in the internet was turned into knowledge graphs. It was turned into entities. It was turned into relations. And once the information out in the World Wide Web was converted into machine readable and machine interpretable graphs, this led to the development of RankBrain, which happened in 2015. Next, because of these developments, Google was able to introduce Hummingbird, which was a system that was able to operate at the meaning level. And more recently, we ended up with BERT, which used transformer architecture in order to represent and process language. Now, before we get to our working examples, I have a question, and I would you can answer by unmuting yourself or by putting your answers in chat. If you were a query answering expert, and someone was to throw the query at you, what is Dune? What would be the information that you would need in order to answer this question? So think about how we would process these three words, and what would give us all of the context that we would need in order to provide a usable response to our user. Now, this could be facts. It could be other related topics. That's right, Randall. So first thing is, in order to provide context, we're going to think about maybe sand dunes. And of course, the meaning of the word dune in the constructed in the conlang used in the movie franchisee. So of course, we have the movie. This could also be, I mean, if we are going to provide our user with the history of this word, what else would we need to provide? One of the things that we might consider is the book series, which started all of it. A related entity to the word Dune could be the author of the series. Maybe Timothy Chalamet might feature in your response, or some of the other famous actors who are part of the latest movie franchise, right? So we have a word, and when we are using our own system of language processing, our brain, to find a usable response to a query, we are trying to call on all the relations that we can think of. And at this level of facts, we have already, just with a simple 3-letter sentence, we've already accessed information that goes back about 3 decades, right? And there is going to be some kind of processing that we're going to need in order to take all of the information that goes back about 3 decades and turn it into something that might be a couple of sentences or a paragraph long, because we'd like our user to stay with us and not lose interest, right? So while I set up the next part, I'd like you to think of some of the more a question that someone might have asked you very recently involving facts, and consider what your search engine queries were like. Maybe you were asked about libraries, the library's timings, or you were asked about what your specific discipline does. And think about all of the ways in which you as a human responded by creating connections, and think and consider how challenging it is to translate or create an analogy of our way of processing information to suit billions of data points, billions of documents, and operate within seconds rather than hours. So for the next part of this talk, I'll be discussing some working examples. One of the things that I'd like you to keep in mind is, in order to set up these working examples and have them executed in the span of a couple of minutes, I had to restrict how much data I was feeding the system. And so even if you might notice that as you play with the amount of data that are or number of documents that our system receives, the output of our system to search queries is going to vary considerably. So it's sky is the limit if you're if you download your own language model, if you have access to a heavy GPU, you'd be able to see demonstrations of semantic search that are absolutely amazing. And in this case, we're going to see a very small example of how semantic search works. And while we are looking at what is working and what's not working, consider what it means to be able to provide thousands of billions of data points to a system. Just give me 1 second. Let me make sure. All right. So the first pre-trained system that we are going to be calling is Cohere. So Cohere is an AI platform. It does a lot of interesting research. And one of the things that we need to use for today is a embedding model. So we want the language processing side of the semantic search to already happen, because we may not need to actually do it for each one of our use cases. And so this creates an out-of-the-box, a very simple out-of-the-box system that you can execute in a matter of minutes. So at this point, if you're keeping, if you'd like to try the code as I go through the demonstration, you will need an API key. as I announced in the beginning of the workshop. And if you have it already, maybe it might be a good idea to just copy it and keep it in your clipboard. All right. So if I had to build a simple semantic search engine and use Cohere's models to do it, um, consider what kind of input data would be suitable to a task like this. So let's say you have access to every question that someone has answered on Stack Overflow, along with every answer that the person who asked the question accepted. Right, so you have questions, you have answers, and on the back end, if those of you who use Stack Overflow would know, when you ask a question, you always get a whole list of related questions that pop up. So if hypothetically, if I had access to Stack Overflow's entire corpus, what would I do in order to build a semantic search that would answer questions for a programming language? So a breakdown of the steps would be: first, access this archive of questions. Unfortunately, I do not have it. Next would be to find a way to create embeddings so that I can power my semantic search with it. Third is I need some kind of a search function that uses an index so that all of our information can be retrieved in a speedy manner. And we would need a nearest neighbor search system so that we're looking for things that are related to each other. And finally, we would need some kind of an output system that returns, for example, returns all of the questions in the question bank, which are very similar to the user's query, so that a user gets more than one web page to access at the same time in order to have the best possible user experience. Right. So we will look at the breakdown of these steps and see what it looks like to execute this. Right. So first, the first thing that we would need to do is get some installations and import some libraries so that our Python system has everything that it needs. And while this happens, I am going to look at the next step. And in case you see me pausing and waiting for the language model to load, this is the fastest possible manner in which I could set up this demonstration. So bear with me. Now, the language model part is where you'll need your API. So I have a little commented line in the code, which is just an empty string. So go ahead and put your API key between the quotation marks. Now I'm going to simply input my API key in the form of a text file, because API keys are typically not to be shared. So once you have your API key and all of your imports are done, we will start by examining the data set that we're going to use today in order to power our semantic search. So today we'll be looking at the TREC data set. This data set is a well-curated, well-researched data set where questions are mapped to their categories. And in order to access this data set, we're going to use we're going to use the Python datasets library, which gives us an opportunity to access data sets from Hugging Face and download them in a clean manner, right? So this would be my load question. Now, while this loading is happening, it's not going to proceed unless you say yes. It's just a little setup that I have to make sure that we don't end up downloading insane amounts of data. Next is, if we want to inspect the data set, we can simply use the .description function, and this basically fetches the description of the data set that the author basically added on Hugging Face. Sometimes you might see, depending on the data set, this might turn an empty string. It happens on occasion. Next is we're going to actually download the data set and basically get the train split. So because every model is going to have the data is going to be split up so that you can train and test your model. We're just interested in the training data. So that's all I'm downloading. And if your downloads has happened correctly, you're going to just see a little table of sorts where we're going to have first we're going to have some kind of index for our questions, and then there's going to be a series of questions, and then there are some labels on the side which are for the relation. Next, we need our data set to go from being a human language into being machine readable embeddings. And for that, we're going to use our Cohere model that we downloaded to convert our data set into a set of embeddings. Now, the next couple of steps might take a little while. So in this case, let me go back just a few steps. I did not import the entire data set. It's got a lot of entries. In order to save some time, I'm just looking at the first 3,000 words. Sorry, 3,000 rows. And because my input data has 3,000 rows, when you look at the shape of your embeddings, you're going to be it should return 3,000, 1024, which tells us how many entries our model took, and how many features it returned per input. All right. So next we actually create the index. And for creating the index, we're going to use another tool called Annoy. And what this does is it turns all of our embeddings into something that we can swiftly call, and this improves the response time of our system. All right. So once all of this is done, we will move on to providing a user search. So in this section, I provided a bunch of sentences. Now, the reason why I'm asking a question about the presidency is because I have only the first 3,000 rows in the data set. So it may not have information about absolutely everything on the internet, but I am relatively confident that some information about the United States might be available in this corpus. So, all right. Now, as soon as I run this, my output is going to be a bunch of queries that are saved in my data set that seem to be related to the entities in my query. So in my query, the questions, the words president and say US might be extremely important. And so some of the questions in the 3,000 questions that I was providing the model, we have the Democratic nominee for presidential election, US president, a question about a former US president, something about White House and ghosts. And there are also some interesting questions here that may not be directly relevant, but remember, this is a garbage in, garbage out system. And so depending on what kind of data we provide our system, that is what's going to power our search. And in this context, if we have a small and limited data set, if I'm only using 3,000 sentences where some contexts are discussed, this is going to reflect in our output. So the smaller your input, the more constrained your semantic search model is going to be, and that's what's going to impact our outcomes. And compare this to, say, a Google or a Bing search, where you could ask about anything, and imagine the kind of information that you get back. And one of the things that we keep in mind is how much information do we provide. So just Randall, let me just look at your question. Thank you. So the numbers that my model is outputting is the distance. So this tells us how close our model thinks a given question, a given response is to the user query. So because our query is who is the president of the US, the closest response that the model thinks is eligible is the first one, which is who was the Democratic nominee in the American presidential election, which with the distance of 0.9. And as you can see, these are all of these the responses that we get from our semantic system are ranked. So the response that it thinks is closest to our query will be on top, and then we kind of go down. And right now it's providing me with a finite number of responses, and that is also something that I can that I can set up. So here in the create the search index code, I've set up and I've requested that my code only return 10 responses. So this is also a number that we can play with. If you'd like a more broader search, you might want to add 100 or 50 or 20, and I invite you to try out some of these settings to see what happens. Now, another potential use case would be to use the Wikipedia corpus. Now, the Wikipedia data set is a bunch of topics. So if you consider the structure of a Wikipedia entry, we have a title, right? And following the title, we have a whole bunch of text that is somehow factually related to the title. Now, for those of you who have created Wikipedia entries, when your the text does not match the title, or if your text is factually inaccurate, the moderators of Wikipedia will get very, very angry. And so even though despite being maybe not the most accurate source of information, given how well curated and open source it is, Wikipedia is also a great way to power semantic search. So for this example, we're going to use Torch, which is PyTorch, which is a very popular Python library for deep learning. And instead of loading the entire Wikipedia, we're going to limit our loading to 5,000. And in this case, I'd like you to, again, if you're also following along, consider changing 5,000 to say 10,000, or moving it down to 2,000. And or if you have your own, if you're working with a GPU, you can even scale up and see how the quality of our semantic search responses changes with it. All right. So I'm going to quickly check. And as you can see, I requested 5,000 documents. And so the embeddings model has 5,000 entries, and each entry has a 768 features. Next is we're going to just provide our query, and this is the code box where you can, instead of Albert Einstein, if you'd like to ask something else, if you'd like to find out what information lives in the first 5,000 documents in Wikipedia, this is a great way to find out. Right, so here, if I run this code, it's just all I'm doing is providing a query, setting up my response, and telling my model to return the top 3 options, top 3 Wikipedia documents that relate to the question, when did Albert Einstein die? And so we've got 3 paragraphs here. One, it tells me about the death of Einstein's son. So vaguely related, but I think our model took a wrong turn somewhere. The second one is a paragraph on when Albert Einstein was born and when he died. So definitely a lot more useful. And the third return that we got is, if we look all the way till the end, it's telling us about the exact date of his death. And it also tells me how he passed away and what he was doing hours before he passed away. So, oops, sorry about that. So we got some useful information out of even just by calling the top 3 most relevant search results, we're already in possession of the information that we were seeking from our query. All right. Right. So some of the discussion on limitations, right, we got information in a lot of these cases just because of the way I set up the response in the first case. In both cases, we're just asking for the actual document where the information lived. So we in this case, I did not create a nice, beautiful format, but there are ways to use to power another language model to synthesize all of this information, create a little text summary, and provide it to the user. So what do we want our information to look like is a question worth considering. Next is the data set. Again, the size of the data is going to determine how much information and what information we can get. Third is ranking. We our setup is telling us how close it thinks a document is to our query. It's something worth investigating when building your own semantic search. Finally, here's a little visualization of all of our discussion on distances and closeness and similarity. It might take a couple of minutes. And while this loads, I'll just briefly discuss our second example for powering semantic searches, which is DistilBERT. Again, as I mentioned, BERT is just a cool, nifty tool that was able to find relations between word. DistilBERT is a smaller, is a model that is relatively small compared to the entire BERT, and it's something that is relatively straightforward to run on your own system. And just here's the search. If you've been able to load the plot and you move your cursor along the plot, you'll see which questions are related to which other questions. So here is just a neat map of where all of the information lives and what gets called when a specific query prompts our system to return information. Now, for DistilBERT, we're going to need some more Python libraries for the setup. And just in the interest of time, I'm going to quickly load our model. It will take a few minutes. It is a slightly bigger setup. Right. So in this example, I'm using Cora. So those of you again who are or were Cora users, you'll know that it's a data set where people ask questions, and there's a crowdsourced way in which responses are sought, and there is a moderation mechanism that tries to make sure that questions and answers are related to each other, but it's a lot more organic and than Wikipedia. And of course, once we set up all of our system, we will be able to download our data set from its source. Again, I'm setting my corpus size to 10,000. I'm keeping it small. And then we're getting all the unique sentences from our corpus, and that is our setup. Next, we need to take a moment to create the embeddings, and that is where DistilBERT comes in. That's our model that's going to convert the Cora data set that we just provided into something that a machine can read. Right. So I will just take a quick pause here while the encoding happens, and if you have let me look at some of the questions here. Yes, Randall. So there are loss functions involved in the actual language model. In our case, in the case of how the output reaches us, we're using nearest neighbors as our search option. So when you see a low score, it just means that there's more nearness. Just give me 1 minute. All right, so with 10,000 documents, it took about a minute, I'd say. If you have more data, it's going to look differently. And if there's too much data, then Google Colab is going to be very angry with you. So I recommend doing it on your own system or with a GPU. Next, we're setting up a little function that can actually give us the process our query and return us a response. And I have two, again, because I'm limited by the first 10,000 documents that the data set was able to grab, I am uncertain of what information lives inside those. So I'm just going to ask two questions and see what happens, right? So as you can see, by providing the search, how can I learn Java online? I was able to get a couple of Quora questions that are relatively related to how Java works. And again, for France, if we actually look at what kind of responses we got, something about the capital city, right? So that's very, very related. And on the left, you have numbers which tell you how close the system thinks a given question, Quora question, is to our actual query. So we've got landmarks, not sure. Then you've got some classified sites, then things that you find in France, but not in the US. So just a reflection of what exists in the first 10,000 documents in our data set, right? Now, in the previous workshop today, there was a fantastic discussion on how large language models can be used with Olama. So in the interest of time, I won't be able to cover it, but I have included an optional collab notebook where where I've given an example of how to run semantic search with Olama. I had to do a lot of research, tricky research, to figure out how Olama can be run on Google Colab. So I apologize if this code gets extremely buggy. But essentially, we download an embeddings model that lives on Olama. I provide it with 50 sentences on the history of Google, and then I ask my semantic search model about a bunch of questions about Google, like which country is Google in, and so on and so forth. So if you have time later, I invite you to try this notebook out and consider the three kinds of data sets that we looked at today, right? We looked at, or four, I should say. We looked at a well curated data set which had all kinds of questions in no particular order. And I scraped about 5,000 of them. We had a Wikipedia corpus where I had different paragraphs from different Wikipedia entries, and I was able to I used a semantic search model with Wikipedia documents. The third one was Quora, and here the fourth is a user provided document. So you as the user are going to be giving it a document and asking questions. And we've also used three kinds of models. So something here to think about is, in case of, depending on what your use case is, are you looking for a semantic search model that returns responses that are kind of whimsical and fun? Quora might be a good data set. If you're looking for something more serious and more information oriented, but you don't need the information to be in depth, Wikipedia might be a good answer. And of course, if you're running things, if you have data that you'd rather run on your own time, and you'd like your control over the model, and you'd like to do it on your system, Olama is a great option. Okay, so let me just look at my time. Okay, now there are a couple of at-scale demos. Now, these may not be exact demonstrations of semantic search, but these are just some very interesting tools that Google has provided that Carlos brought to my attention. So these it's a product from Google Research, where if you click on it, it'll take you to a page that says semantic experiences, and these are just some nice user-friendly at-scale demonstrations in understanding language. So some of these are verse by verse, where you can basically compose a poetry in the style of classic American poets. So that's the kind of documents that went into it. Then you have a semantic search or an interactive search that you can conduct with a corpus of books. I imagine Google Books was the data set used here. Then we have semantic reactor, where there are some experimental work with machine learning models, specifically with data from Google Sheets, right? And there's also an option for you to create your own semantic experience. It's all relatively user friendly, so I invite you to give it a try. And one of the tools that I thought was a lot of fun was Semantris. which is a semantics-oriented word association game where your ability to add words results in the Tetris blocks falling into place. Now, I've had a lot of fun with this, but I am not good at it at all. So I'm going to just click on it and give you a little demonstration. And I apologize for the quality of my gameplay. All right. Okay. Okay. Maybe the last one. Oh, sorry. I'm being blocked by my captions. Give me a minute to get rid of them. How do you... Oh, well, yeah, there we go. Let's see. Oh, sorry. There we go. All right. Try something else. Okay. What would be the next word that comes to mind? I'm thinking pencil. All right. Okay. That helped sort my words in a different way. Okay, so now I'm looking for something related with pencil that is out of these options. Oh, unfortunately, I was too slow, so my score was pretty low. I invite you to try it out. And essentially what this would demonstrate is what word relations you see versus the kind of word relations that Google was able to find from all of the information that thousands and billions of users have provided it over a course of time. Right. And at this point, just a thought that I'd like you to leave with. Think about what it takes for humans to understand language, right? If I have a very short, like just based on the 1 hour discussion that I have had with all of you and the information that I have provided you as far as semantic search is concerned, there are so many creative things that linguistic things that you can do with this small amount of information, which is just sentences uttered over a course of 50 minutes. In order to create a system that is even comparable to how humans use language, we've needed billions of parameters and all of the information that lives on the World Wide Web from its beginning to current days. And that is a way, that's just how difficult it is to translate or convert human language into something that is machine readable and machine interpretable. And and in order to get to the point today where you can have a almost real life like conversation with ChatGPT, that's how much information we've had to process and provide. And going forward, like as far as the research on this is concerned, people are looking for small language models. People are trying to add more efficiency, add more simplicity, and all of it is just it comes down to a question of how we're able to process language in order to find relationships between words and find a way to utilize all of the information that users are providing into a way that our machines can understand. So that is my very basic, very simple introduction to semantic search. I have a couple of added readings, as well as there are lots of links that are spread throughout the notebook for all of you to learn some more. Next week, we will be looking at, let me just check our schedule. Or I should say schedule. Next week, we are looking at information extraction. So it is, in a way, a continuation of our discussion on searching, except we're going to be looking at how components that build information extraction are built, and why information extraction is important, and some of the pieces, the building blocks that get us to efficient information extraction. So I hope you'll join me next week. This is the Data Lab series, NLP for All. And thank you very much for your participation today.